So where we left off in the last video was we said that the power, we calculated the power to be the electric field dotted into the electric current and then integrating over that volume of the system. So now let's apply Maxwell's equations to this. So first we'll start with the Ampere-Maxwell equation. So the current, if we divide both sides by mu naught, is the curl of the magnetic field divided by mu naught minus E naught mu naught divided by mu naught, the change of the electric field with respect to time. Okay. So now we'll dot that with the electric field. So I get the electric field dotted into the current is equal to the electric field dotted into the curl of the magnetic field divided by mu naught minus E naught, epsilon naught, the electric field dotted into the time derivative of the electric field. Okay. Okay, so let's do some vector identities. So if we look at the first one, this electric field dotted into the curl of the magnetic field, I can rewrite as the B field dotted into the curl of the electric field minus the electric field dotted into the curl of the B field. Oh, sorry. Let me fix that. So, I'm sorry. So the first term is, if we start with the divergence of the electric field crossed into the magnetic field, okay, that's what I wanted to say. So the divergence of the electric field crossed into the magnetic field is the same thing as saying the magnetic field dotted into the curl of the electric field minus the electric field dotted into the curl of the magnetic field. So this is the term that we're interested in. So therefore we can write this as the B field dotted into the curl of the electric field minus the divergence of the E field crossed into the B field, like so. Okay. So that's good. So we can take this and put this into the previous equation. Now we can also do is take a look at Faraday's law, which says that the curl of the electric field is equal to the minus the time derivative of the magnetic field. So we could take that, put that into here, and we come up with an equation which is the electric field dotted into the curl of the magnetic field is equal to the B field dotted into minus the time derivative of the B field minus the divergence of E cross B. Okay. Well, what we could do is rewrite these time derivatives, because we've got a B field dotted into the time derivative of the B field, and in the previous equation right here, we have the E field dotted into the time derivative of its E field, and so we have pretty similar equations. So what we could do is reduce it further by saying the magnetic field dotted into the time derivative of the magnetic field would be the same thing as taking the derivative of B squared, so B dot B, and then putting in a 1/2. So basically what we've done is we've brought the dot product inside the time derivative, but in doing so we've, basically by the chain rule would have two of them, so we'd have divide by 1/2. So this would give us 1/2 the derivative of b squared. So you get rid of the dot product. You now have b squared. The same thing would be true for the electric field. Now we get 1/2 the derivative of e squared dt. Okay, so let's put all this back into our equation for the electric field dotted into the electric current. So I now have, let's see, minus 1/2 the derivative of epsilon naught e squared plus b squared mu 0 minus 1 over mu 0 the divergence of the electric field crossed into the B field. Okay. Okay, so you basically collect terms, which is nice because now we're getting basically the time derivative of the energy density and this extra term, which is the divergence of the two fields crossed into each other. So that's kind of interesting. So now we'll put that all together and say that the power is equal to minus 1/2 the time derivative of, well, sorry, let me go back. So let me try this again. So the power, we have to take that e dot j and put it into the integral. The power is going to be minus d dt, the integral over the volume of 1/2 epsilon naught e squared plus b squared over mu naught, integrating over the volume, minus the time derivative of 1 over mu naught, the integral over the volume of the divergence of the E field crossed into the B field, integrating over the volume. Okay, so now what we see is that I can use the divergence theorem on that second integral, and I would have, so if I rewrite things, so let me say minus d dt, the integral over the volume, 1/2 epsilon naught e squared plus b squared over mu naught, integrating over the volume, plus 1 over mu naught, integrating over a closed surface, or the closed area, of E cross B dotted into that area vector. Okay, so if I look at this, what do I have? What I essentially have is what's called Poynting's theorem. So I now have these two terms. I have a volume term, and I have a surface area term. And so inside the volume, I've got the energy density. So the energy density inside the volume is what it was before, 1/2 epsilon naught E squared plus B squared over mu naught. Okay, but now I also have this energy term associated with the surface. And that's basically the energy that's flowing out of the system. So the energy flowing out of the system is minus 1 over mu naught, the integral through the surface E cross B dot dA. So it's the amount of energy that is exiting the system. And that is often called the Poynting vector. Where I would have S is 1 over mu naught. The electric field crossed the magnetic field. So it's an energy per area, or an energy flux density. So it's the amount of energy going through that area. So it's a flux, and it's also a density because it's inside the area integral. So in the end, the power equation that we get is minus d dt, the integral over the volume of the energy density, minus d dt, the energy through the surface of the Poynting vector, right here. So this is the energy associated with charge, and this is the total energy associated with the fields. So inside the fields, so on the right-hand side, the only thing in there are fields, electric and magnetic fields. On the left-hand side, we found that by looking at the Lorentz force and seeing it push a charge over a certain. So we see that on the left-hand side, that it is the energy associated, or the work of a force, the Lorentz force, pushing a charge over a certain distance. So in the next video, we'll continue this discussion a little bit more. Well, after one more thing. So if there are no charges, then the left-hand side is 0, and we'd essentially get minus d dt, the integral of the energy density, and the integral of the Poynting vector. And essentially what you would get is the continuity equation for the fields. I would get, I could rewrite this with the divergence back into a volume integral, and I would get the time derivative of the energy density is equal to minus the divergence of the Poynting vector. So now I've got a second continuity equation, related to energy and not just charge. So we now have two conservation laws, conservation of charge and the conservation of energy.